Finally, we will see the numerical computation of the Jacobian. For a complex robot, it can be very tedious to manually compute the Jacobian. So an alternative approach is to compute the Jacobian numerically, that's to say, to use a numeric differentiation method. The Jacobian, if we only consider positions for an n degree of freedom robot, is given by this expression. The important part of this expression is to see that each column is a variation with respect to a given angle. For example, this first column is a variation with respect to Q1. The second column is with respect to Q2, and so forth. The last column in this case, considering an n degree of freedom robot, will be the variations with respect to Qn. We can now call xyz something like xp. So we will say that this column will be just the derivative of xp with respect to Q1, then xp with respect to Q2, and so forth, where xp is the position, x, y, and z. But we can also represent the position as a function of forward kinematics. So this is actually a function of Q1 up to Qn. Then we can approximate the derivative of the position with respect to joint Qi. Basically, we have here derivatives, so we want to approximate each of these derivatives. For approximating the derivative, we have to use the definition of the derivative. So this is the partial derivative, and this is approximately equal to the increment of xp divided by the increment of Qi. In this case, the increment will be this f evaluated at all the joints, but for the ith joint, we sum a delta of Qi, and then we subtract the f of all the joints and divide by this delta of Qi. So this delta Qi is going to change. If we are, for example, in this case with Q1, this will be the first one, Q1 plus delta Q1 over Q1. If we are in this case with respect to Q2, it will be just Q2 plus delta Q2 over delta Q2 and so forth. Let's see an example. Consider the following forward kinematics, which we have seen before. Actually, this is from the RR robot. And we want to compute the Jacobian numerically when the joint values are Q1 0.5 and Q2 1. The solution is the following. We have that this is the expression for the Jacobian. Let's take first these derivatives with respect to Q1, which are the first column. For the first derivative, we just apply the definition. For the first case, this element is just the same function because they are a function of two joints. We only have Q1 and Q2. So it's a function of two joints, but since we are taking the derivative with respect to Q1, we just add this delta to this Q1. So it's Q1 plus delta Q1, Q2 minus the function at Q1, Q2, and we divide it by delta of Q1. We are replacing then the expression. So fx is this expression, cosine, cosine. We have cosine and then Q1 plus the delta Q1, Q1 plus the delta Q1, and we subtract the original expression. And then we do the same for the derivative of fy. It's exactly the same. So here again, only Q1 has the increment. We just replace, so it will be the same thing, but now with signs. So it is the same thing with signs. And that's it for the first column. For the second column, it will be similar. So for the second column, you will have to take the derivatives and again apply the definition. So in this case, the derivative of fx with respect to Q2 will be the same derivative, but now we have to increment Q2, Q2 plus delta Q2. And we replace the values and we get this expression. We do the same for the other one, for fy. Only Q2 has the increment now, and we divide it by the delta of Q2. And we replace it the same thing, but now with signs. Now let's use a value of delta Q1 and delta Q2 of 0.001. We usually want these values to be very small, because if you remember, the derivative is the limit when these deltas tend to 0. So the smaller, the better that we have. If we do that, I'm just replacing all the values, we will get these numbers. You can just replace all the values and you'll get these numbers. And then using these numbers, you can generate, or you can order this and get the Jacobian. Now this is the Jacobian, numerically computed. Just for comparison, I'm putting here the Jacobian that we can compute analytically. And in this case, analytically, we have this solution, but numerically, we have this one. You can see that they are almost the same, or they are the same for practical purposes if we don't consider the rounding errors. If we want to do that in Python, we have to define the forward kinematics function, and then we have here the computation of the Jacobian. It would be easier first to obtain the transpose of the Jacobian because we want to compute this delta for every column first, and then we just transpose that to obtain the Jacobian.